Let us now look at some specific examples of constraint maximization and minimization problems. So, for example, this is a modified version of the example in the book. Let's suppose we have to maximize x times y. So, you have to choose x and y to maximize x times y subject to the constraint 2x plus y is equal to 10. So this is like your utility maximization problem only, where this is your utility function u of x comma y. It is a function of goods x and y. The price of x here, this is like your budget constraint, where the price of x is 2 and the price of y is 1. So let us set up the Lagrangian. The Lagrangian here is x times y plus lambda times 10 minus 2x minus y. Okay, and if I look at the first order conditions, partial L by partial x is going to be equal to y. So here if I take the derivative with respect to x, that's y, minus 2 times lambda is equal to 0. We put the first order partials equal to 0. Let's call this equation 1. Partial L by partial y is equal to x. Then I get minus lambda, put that equal to 0. Let's call this equation 2. Then we have partial L by partial lambda, which then gives us a constraint. That's 10 minus 2x minus y equal to 0. Now we have some important pieces of information hiding in here, in these three equations. So if you notice here, from equation 2, we can straight away infer that for the stationary point in equilibrium, our lambda star is going to be equal to x star. So anyway, this equation implies that lambda has to be equal to x in equilibrium. Also, if I do the standard procedure of taking the ratio of equations 1 and 2, I'll get, so from 1 and 2, I'm going to get the result that y by x has to be equal to 2 lambda divided by lambda, which is nothing but 2. So it must be the case that in equilibrium y has to be equal to 2x. So now let's do this. Let's substitute this information into equation 3. So once I do that, if I substitute y equal to 2x into equation 3, I get, so 3 implies 10 minus 2x minus 2x is equal to 0. I've just substituted for y here. And that then implies that in equilibrium, so I'm just calling it an equilibrium in the sense that we're now heading for the stationary point, but we still don't know if it's a max or a min, for which we'll have to look at the bordered Hessian. So I have x star is equal to 10 by 4. So 10 is like your money income here, divided by 4, which is 2.5. And that by this condition here, lambda has to be equal to x. So that has to be equal to lambda star. And this then implies that y star, let me just move this up. So in equilibrium, it must be the case that y star has to be equal to 2 times x. So that's going to be equal to 5. So a stationary point, note here that because you have 3 choice variables, the stationary point is going to be specified in terms of x star, y star and lambda star. Don't forget the lambda. So that's the stationary point is 2.5, 5 and 2.5. This is your stationary point. But remember that the first order conditions are just giving you information about the stationary point. We still don't know if it's a max or a min, for which we have to check our bordered Hessian. Now the bordered Hessian determinant is given by, if you remember the formula, that's 0, g sub x, g sub y, g sub x, g sub y, and then the standard Hessian kind of a matrix inside, lxx, lxy, lxy, lyy. So basically this is like your Hessian in the chapter 17 framework, which is bordered by this 0 g sub x, g sub y. That's why it's called the bordered Hessian. Okay, now what is our bordered Hessian? Now, if you go back to the problem, this was our original problem. Let me remove this old sheet. Okay, in this problem, 2x plus y represents my function g of x comma y, right? And xy represents my function u of x comma y, or the original function f. So anyway, the function g of x comma y, let me just put it down here in one corner, g of x comma y was 2x plus y. So our bordered Hessian, g sub x becomes 2, g sub y will be 1, the border will be 0, constituted by 0 to 1. Now what is Lxx? So if you go up, look at the first order conditions. L sub x is y minus 2 lambda. So Lxx, the second order partial derivative with respect to x, would be 0. And the cross order partial would be 1. So let's put in these numbers here. 0, Lxx is 0 and Lxy is 1. Lxy is 1, and what is Lyy? Now L sub y is x minus lambda, so clearly Lyy would be 0. So let's evaluate this determinant, and because here we don't have any terms containing x or y, we don't have to substitute for the information that we have here from the stationary point. We just have to calculate the determinant value. So that's going to be equal to 0. The first term will be 0 minus 2 times, I'm doing the Laplace expansion, minus 2 times 0 minus 1 plus 1 times 2 minus 0. So that's going to be 2 plus 2, which is equal to 4. And as I told you in the previous video, the second video, that if the bordered Hessian, the determinant of the bordered Hessian is positive, you can conclude that you have a max at the stationary point. So here we have maximized at 2.5, 5, 2.5. We have a maximum for this function. Okay, now what I'm going to do is, what is important here really is that you should also have an intuitive sense of this problem. You have actually done all the math and you have got a max at this point. Let's see that intuitively, let's see if intuitively also we get a solution around this point. Let's do that through a graph.